All right, so y'all can hear me down there. And what I was doing right there was setting up a service that Google provides that basically is streaming the context of this lecture, and it'll create a YouTube link to it. So I like to do that before each of my lectures. And I had planned to do that before class, but they were still trying to work out the IVN. We got that all taken care of. And one thing to be aware of, it looks like you did finally get it, but it took us a little while to call down there. The system used to automatically connect, or in other words, it was just automatically ready to go. Now there has to be somebody in the classroom to click accept on your end. All right. So we're just going to get started. Today we're going to talk about a few more background concepts that we need to learn in order to create maps. We talked about scale a bit last week, and so today we're going to move on. Talk about coordinate systems, basically. Sometimes the words coordinate system and projection get used interchangeably. They're not exactly the same thing, and we'll talk about that today. This may be a lecture where, if you're in the GIS class, there's a little bit of duplication. Material presented here. You get some good stuff out of it. All right, so latitude and longitude. Lots of geographers have already learned about that. I'm going to spend a few minutes talking about latitude and longitude. So, what is latitude and longitude measuring? Degrees. So degrees is usually what type of a unit? Are we measuring distance with degrees? Angle. That's right. We're measuring angle, and you said from the center of the Earth. Okay. So there are some slides on this, but from the center of the Earth, we're measuring an angle. So for the degrees of latitude, which ones are those? Kind of make my arm do this. Yeah, horizontal. Okay. And do degrees of latitude ever intersect with each other? No, they don't. They run around the Earth like hoops. So they get smaller and larger, and they're actually measuring the angle from the center of the Earth up to that point on the sphere. Okay. We'll talk today about how the Earth isn't really a sphere, but it's pretty close. All right. So sometimes we call those parallels. They're always parallel to each other. They're evenly spaced. They would be perfectly evenly spaced if they were on a sphere, but they're not. So they're fairly evenly spaced. But because the Earth is really a little bit wider than a sphere would be, if it was a sphere, sphere would be a perfect ball. They're not exactly perfectly spaced, but they're a lot more perfectly spaced, or a lot more evenly spaced than the other lines, the ones that run from north to south. Sometimes get called meridians. Sometimes they get called longitude. They are they converge at the poles. And if you're following one line of latitude around, they're evenly spaced. But they get closer together to each other at the poles. So they make like, the way I always like to think about it is if you have an orange, you peel the orange, you hold the top and the bottom of the orange, they're like the little lines that are in the sector. You pull a sector out, and that would be between two different meridians or two different lines of longitude. So one important distinction here, particularly as cartographers, if you want to make flat maps, is that degrees of longitude change in terms of the distance between the degrees. Okay? And so if we want to make a flat map, that's a problem. If we want to use those as coordinates, we introduced the concept of coordinates last week. A coordinate is a way to numerically reference a location. All right, so these are I'll do it over here. These are the lines of latitude, the parallels. The ones running this way are meridians or lines of longitude. All right? Okay, the Earth here. You can't see the cursor. Is there a way to make it so it mirrors it instead of? Okay, yep, that's what I wanted. So I'm seeing what you're seeing. So the recording is seeing the same thing as you are. All right, so the Earth's dimensions. So as I mentioned, the Earth is not a perfect sphere. It's slightly wider than it should be. Okay? If it was a perfect sphere, not that it should be a perfect sphere, but if it was a perfect sphere, it's a little bit wider. You can see it's not much wider. We've got a distance of 7,926 miles through the equator and 7,900 miles through the North Pole. Okay, so that's really, really close. Not that you'd want to walk 26 miles, but if you think about what percentage is that? You know, divide 20 by 7,900, and it's less than 1%. Okay, we talked about latitude. I think we got that down. Do you have any questions? Let me know. All right. What are the zero lines for latitude and longitude? Many of you probably know this, but let's just make sure everybody's up to speed. Latitude is the equator, and longitude is prime meridian. Where is the prime meridian? It runs through Greenwich, which is a suburb of London. Okay. The United Kingdom was a world power at the time, and they set the Greenwich Observatory as the not that they aren't a world power, but they set the Greenwich Observatory as the zero mark. It's pretty convenient because the other side of the world is basically empty as well. So it's not the only reason that was the zero mark. And it's convenient to have the other side empty because of time. Now we're only a little bit concerned with time as cartographers, but time is an important thing. And the international date line is at the other side of the zero line. Okay, and you get there at that point, and you cross from one day to the next, just crossing the line. It's a whole 24 hours different than it would be on the other side of the line. So it's convenient that was on the other side. Okay, a few other implications of this coordinate system, which we're going to give a name here in a second. This coordinate system has a few things. Here we've got a diagram showing basically a small circle and a great circle. And a great circle is any circle that's plane. So a circle creates a plane, or only one plane can pass through a circle is another way to say that. Any circle whose plane passes through the center of the Earth is a great circle. Okay, and we can have an infinite number of great circles, but every line of longitude, the ones that run north-south, every single one of those is a great circle. However, only the equator is a great circle running the other direction. Okay. Any other circle that you can create around the Earth is referred to as a small circle, one that does not intersect the center of the globe. We call these coordinate system, this coordinate system that we came up with, a spherical coordinate system, or spherical coordinates. Okay? So when we reference using latitude and longitude, and this is the same thing I was trying to say, okay? We've got latitude being the angle from the center of the Earth, and the longitude, the angle around the pole that would extend through the Earth. Okay? So we're measuring angles. And we call those spherical coordinate systems. Oftentimes, there's another name for them. There's always like two names, at least in this lecture. There'll be two names for lots of different things. So spherical coordinates are one way to describe them. And since the Earth isn't a perfect sphere, sometimes the term geographic coordinates gets used. That's what gets used a lot in your software, but not always. So in the software that we're going to be using, geographic coordinates. We've had enough pictures of them. Okay, so if we use this latitude and longitude coordinate system, or the geographic coordinate system, to measure locations on the Earth, it's okay and it's great. It works really well for measuring points on the Earth. And you see that it's not, as we go through the lecture, you'll discover that just because we have a latitude and longitude for a location, there's still some additional questions to ask. Because measuring the Earth itself is a big problem to tackle. The Earth is really, really large. What's this based on? It's based on the center of the Earth. Finding or quantifying what the center of an object that's not a perfect sphere is difficult. And so there's different measurements taken to reference what the center of the Earth is. Okay? But setting that aside for a second, we will learn about that. Setting that aside for a second, we can still use this coordinate system to measure locations, and it works well. However, when we try to make a map of the Earth using these coordinates, there are some issues, some pretty big issues that we need to talk about. So we have here the globe, and we could take these latitude and longitude lines and just pretend that instead of spherical or geographic coordinates, they were Cartesian coordinates. So Cartesian coordinates, you've heard that term in math before. It just means that we're setting them up in a grid, an evenly spaced grid. So here's the center, the 0, 0 mark, if you will. And it is the 0, 0 mark because it's 0 latitude, 0 longitude. And it's right in the middle, well, not the middle, but it's right in the Atlantic Ocean, the southern Atlantic. Well, not the southern Atlantic. It's south of us, but it's not really. The 0, 0 light mark is right there off the coast of Africa. Maybe the best way to say that. Okay, so if we go around the world like this, right through the equator, and around the world like this, which of those two lines, it's an easy question, but which of those two lines is the shorter line? The more northern one, okay? And so that line in reality is a shorter line, right? And it's a shorter distance. So we can't really use this coordinate system to measure distances. In fact, if we ever wanted to do any other line that was a small circle, that was part of a small circle, any other line like a line that went through here, I'll show it up here, a line that went through like here, it would be pretty much impossible. In fact, that line would really be a curve. Any straight line on this map is actually a curve, an arc. And so measuring that would be difficult. And even if we weren't going to take physical measurements, a map reader would look at it and say that, could misjudge the size of different things, right? Which may or may not be a problem. Okay, if we're using maps for some purposes, it's okay that that we see these distortions. If we're using maps for other purposes, it's not as acceptable. All right, so we talked about geographic coordinate systems, the locations on a map, latitude and longitude. We're also going to learn about other coordinate systems that try to solve these issues. The issue of the world and being able to take true area measurements or true distance measurements, whatever we want to be able to take as cartographers from our maps. So these are called projected coordinate systems. They take the Earth and they project the Earth onto a flat surface. And one way to think about it is that it's kind of like a projector, and that's a projector right there, right? Okay. And if we took a globe, can you imagine a globe in your mind? If it was transparent, it was a transparent globe or translucent globe, and we actually drew the outlines of whatever we wanted to map on that globe, and we had a light source, and then we had a flat piece of paper. That's essentially what we're doing when we say project. We're taking the lines that are on the Earth, projecting them onto a flat piece of paper in different ways. Okay, and a projected coordinate system allows us to come up with planar, Cartesian, projected. Those are all synonyms. Coordinate systems of the Earth, and the big advantage is that we can take linear measurements with these things and calculate areas and do things like that. All right, so we're going to learn about projections. Projections, as I said, are basically a way to represent a curved globe on a flat surface. So when we talk about scale, we talk about making a reduction of scale. The only way to make basically to make a map of the entire world, or even a large portion of the world, that has a perfect uniform scale everywhere, the only way to do that is to actually use a globe. Any other map is going to suffer from distortions. Okay? So the reason that we're learning about map projections is so that when you make maps, you know how to choose a coordinate system projection that will make the best possible map. They'll have the least amount of distortion for what you're doing and for your map readers. Okay? What the map readers, because maybe the map readers don't necessarily care about any particular type of distortion, and it's best to just get the proper angle to display. But you can still do that with a map, with a coordinate system, with the right projection. But maybe you do want to be able to show proper distances and directions. Then you need to pick a good coordinate system. Okay? So again, why do we project? Well, we do have flat maps, we have flat computer screens, and measuring distance and areas in degrees is not only a desirable thing to do, it's impossible to do. You can't say that if you're using latitude and longitude as your coordinate system, you can't use Cartesian math to figure out an area, right? You can't use Cartesian math to figure out a distance. When I say Cartesian math, how do I calculate the distance from one point to another using what we've all learned in geometry? Pythagorean theorem, sound familiar to anybody? A squared plus b squared equals c squared. And you just rearrange the values and you can figure out the distance between 2 points because it's always the hypotenuse of a right triangle. Remember, on a map that's fine, but on the globe, it would be an arc. And so we're trying to minimize the error because there is going to be some error. All right. So most map projections fit into two different categories. And so one of the the big questions that we need to decide when we make a map. Is the intended area is the intended use to preserve equivalence, area, or its true shape, conformal? So one of the trade-offs is between equal area and shape. We can do one or the other. We can't really do both if you want to make a flat surface. So only one can be performed and the other will suffer or lose in its relationship. So some maps are referred to as conformal, some maps are referred to as equal area, and some don't have either tag. And usually what they're trying to do is strike a balance between those two. There's some problems with the area, some problems with the shape. Now, sometimes you'll hear people say that there are, and this is true, there are different things that we're trying to, there are basically 4 different things that we're trying to keep constant in our map, that we would like to keep constant. Area, distance, direction, and shape, okay? But really, these are the 2 trade-offs, because if you preserve true shape, then you're also preserving the direction. Think about it. If the shape is true, the direction is true. That's one of the most famous projections that we'll talk about later that gets used in a lot of maps. The one on the back of the wall there is the Mercator projection. Okay? The Mercator projection, it's a conformal projection. And it was used, the main reason why it was used for so long is for ship navigation, because a line on Mercator was a true heading, true direction. But it's horribly inaccurate in terms of its, let me just pull up. Let me just pull up here for a second, because Google Maps uses spherical Mercator projection. So pull this up. This is what I'm talking about. Okay. So you probably had a lesson like this, but just to make sure. Greenland looks huge. Okay. Mexico looks small. They're about the same size in reality if you were to look at a globe. But this heading, like if I was to leave Mexico and fly or walk or swim across the Gulf of Mexico, I wanted to get to Greenland, that's a true heading. If I measured that angle from north, I could stay on that heading and get to New Mexico. It's a tool for navigation. That's its purpose. And so for the map readers, if the map reader's desire is to navigate, it's an acceptable projection. Okay.
Which projection was that an example of?
The Mercator projection. Okay. All right, so here we have, and it used to be, the Mercator projection is used a lot in web mapping, actually, because when you make, it is hard to make a map of the whole Earth and have it not, I mean, what's impossible to have it not suffer from one of the problems. So there's always going to be a problem. So Google chose that map projection, and it's fine for, especially like if you zoom down into Google Maps and you're just concerned about Hattiesburg. The directions are all fine. You know, if you see something due north of you, it really is due north of you. So that's one reason why it's used that. Okay, so we've got just another example of taking the globe, flattening the globe, and then stretching the globe between these parts. You get a map like this. This is the Mercator projection. Oftentimes you see in the Mercator projection, we just cut off Antarctica because not too many people live there, and Antarctica looks like it's huge, humongous. So you don't always see it there, but it is there. Okay. So it is true nowadays that most GIS software packages will compensate mathematically for the distortions. In other words, it's not the easiest math in the world, but it is easy to calculate. Well, it's easy for a computer to calculate the true distance over the globe between one point and the other. And it's becoming more and more common in GIS software packages for you to, if you click a point and you click another point, it actually calculates the true distance across the globe for those points. And so modern cartography and most GIS programs compensate mathematically for distortions. But that still does not prevent map users from making error judgments, because the projection they're actually seeing on the screen or on the paper is still flat. Okay. All right. So as I mentioned, the term projection actually came from the fact that we are mathematically performing this analog process when we do projections. This analog process. There's a globe, there's some sort of flat surface, and there's a light source. Okay? The flat surface we're going to refer to as a developable surface. In other words, just think of it like a piece of photo paper, which is maybe also a foreign concept to people. But like when I grew up, when you wanted to go get a picture, took a picture and then you took it to the little photo stand and took your film in, and they developed it on the photo paper. Sometimes it could take a week at first, but then by the time I was 9 or 10, 11, they had these places that would do it in an hour. Anyway, so the flat surface is called the developable surface. It gets wrapped around the globe, or sometimes through the globe. Okay, we can make our developable surface, doesn't have to be on the outside. If the developable surface is left flat, okay, it's not covered in this one. That's a planar projection. Okay, planar projection. If the developable surface is wrapped around the globe somehow, we call that a cylindrical projection. By the way, the Mercator fits into the cylindrical projection. If the developable surface is placed over the globe like a dunce cap, like with a cone, conical projection. Okay, so we've got these three categories: planar, cylindrical, and conical map projections. Here's just another diagram from a different book, but still the same thing. Now, like I said, that surface, it doesn't necessarily have to be wrapped around the globe. It can touch the globe in two locations. So the light source can be in the middle of the globe, and it can still be projecting that. Just think of it as projecting it from the other way. Okay? It still doesn't hold up as well, but it's still projecting it onto the surface. So notice how on this cylinder here, it's hitting the globe right there and right there. And on this cone, it's hitting it right there and right there. And on this plane, it's hitting it all right there. So it always forms at least one circle when it does this. Okay? When it's doing the, basically, I'm going to use a math term here, but when the developable surface is tangent to the globe, it's only touching it at one location. When it's a plane, it's a point. When it's either type of one that's wrapped around, it's a circle. All right. So at the locations where the developable surface touches the reference globe, when I say reference globe, remember that this isn't actually happening. We're not wrapping the world in paper, right? It's huge. So when I say the reference globe, we're talking about the pretend globe that's being mathematically created in the computer. Okay? The reference globe, wherever the flat surface hits the reference globe in those locations, there's no scale distortion, but just at those locations. And if you think about it, what's happening here when the projection occurs in this area right here? Well, all of this area has to be compressed and stored on the piece of paper that's running through here, the developable surface. And so it's compressed a fair bit. And then same here, there's some distortion occurring. Sometimes it's compression, sometimes it's expansion, depending on the exact projection parameter. This is fitting onto this, so there's distortion occurring. Right? So it's the most accurate, or the most true to the real scale right here at these locations. And those locations are these two locations in this case. You can tell this is a conic projection because there's a picture right here. But, because it's intersecting the globe, you know. This is a cross-sectional view is what I'm trying to say. Right? Sometimes a planar projection is called an azimuthal projection. You'll see that term used. Okay. So when you see a map, oftentimes the graticule is the latitude and longitude lines, the pattern that they make on a map. There's not always a graticule on every map, but if there is, if you see a graticule that radiates out from a center point, it's usually an azimuthal, well, it is an azimuthal projection of some sort. There can be polar projections, like that start at the North Pole, and there can be ones that start at the equator, but you rarely see that because they have some weird distortions that they would create. Okay, but you see those a lot from the poles. Actually, another one that is pretty common. Sometimes you'll see a map out here. Let's see. Maybe I don't have an example, but I'll pull one of these up. I'll just put this. Should have put one of those in there. Okay, sometimes you'll see a map like this, and it just looks like somebody like jumped and took a picture of a globe, right, or took a picture of the Earth. Okay. Now, this is a fine display of the Earth. We can kind of fill in the fact that the Earth is round. Okay. But this is an orthographic projection. Sometimes in GIS softwares, to make this easier, they just refer to this as the world from space projection. Okay? Now, it's fine to look at, and we can kind of know that Africa curves around like this, right? Africa's not really like shoved and small on this side. Okay? It's the fact that we're looking around the globe. But still, we couldn't use this map to figure out how wide the Sahara Desert is, because the scale is constantly changing as we kind of go around here. So it's just a picture of a globe, and you can make a map projection that looks like a picture of a globe, is the point I'm trying to get across. Okay, and sometimes that's an appropriate map projection to choose for a particular map. Like, you know, you see those in magazines, and you might see those in well, that's another media outlet, but a media outlet might use a map like that, you know, just to show you that it's the Earth from space. In fact, that's really what you're looking at when you go to Google Earth and you zoom out all the way. You're looking at an orthographic projection, which is a planar map projection. In other words, it's just like a picture of the Earth. Okay. So all these map projections have an appropriate use. So we've got cylindrical map projections. We've got conic map projections. Cylindrical map projections are very useful for, like I said, well, this is just one of the things that are very useful for navigation, because direction is preserved very well. Latitude and longitude lines are both straight in cylindrical projections. Okay? Well, that's assuming that you center them either on a line of latitude or a line of longitude, which they almost always are. Okay? All right. Conic map projections are very good at preserving areas, particularly for things that are long and skinny around the Earth. So you'll often see conic map projections. Oh, I forgot to put my computer in. You'll often see conic map projections used to map countries like the United States of America that is shaped longer in terms of its latitude that it takes up than its, than its longitude than it takes up in latitude. It's a wider country. Other countries that are like this are Australia and Canada. So those countries also get, just type in United States of America. Now, I know that in today's world, lots of these maps are going to be, well, actually, all of these maps are conic. And I can tell that they're a conic projection because they curve up here. Okay? It's much more of a pleasing map shape when you see it as a conic. So if you're making a map of just the United States, this looks a lot better. And not just me telling you as a instructor in your cartography class, but this looks better than this. I mean, I know maybe you're saying, well, it doesn't look significantly different, but it's drawn out more at the top because it's not, this distance here is tricking you because it's really not that big compared to like this distance here. Okay, this is a better use of map space because this distance here now is more truly represented as almost the same as that distance. It's a little bit longer, it is, but in the cylindrical map projection, it pulls that out. If I wanted to know the direction to me, it would be better, but if I want to see the shape of the United States in its true form, this is a better map projection to use, a conic map projection. You can see that it's conic usually because lines of latitude show up as arcs. So this arc isn't as long, but these are all lines of latitude, and they do arc a bit because well, this is easier to see. The one that goes all the way from the Utah-Arizona border all the way over here to the the end of the Oklahoma-Kansas border. That's a continuous line of latitude. You can see that it's arc. And then another one picks up here, the northern part of Tennessee, North Carolina. Okay, whereas those would be straight on a cylindrical projection. Sign here. All right. So, like as a little take-home message, if you make a map of the United States as part of one of your labs, you'd want to use one of those projections most often, unless you had a better reason. If you're making a map of all of the continental United States, use a conic projection rather than a cylindrical projection. Okay. So cylindrical projections are good whole Earth maps. They do true shapes. There is very high distortion in size toward the poles, but useful in navigation. I already said all of that. Cylindrical projections. Now, the Mercator projection that we've shown before is not the only Mercator projection out there. Okay, there are cylindrical projections, but there are also transverse cylindrical projections. The most common one is the transverse Mercator projections. Now, these would look horribly distorted if you were to make a whole Earth map of a transverse cylindrical projection. Okay, so what would happen is, let's say we chose Mississippi as the center line, the line that had the least amount of distortion. And we went all the way up from Mississippi to the North Pole and all the way down Mississippi to the South Pole. So that was the line that had the least distortion. And as you got further away from Mississippi this way, there'd be more and more distortion, and it would be bigger. Everything would be bigger and bigger. So it'd be like a butterfly map extending out from Mississippi, and everything would get huge off to the side. So by the time we got out to Russia, it would just be smeared across a big portion of the map. If you looked at Mississippi, it would be small in the middle. Okay, so you're like, well, what good is that? Why would I want to do that? Well, one of the true things about map projections is that it's easier and easier to make a map that is closer to having a uniform true scale the smaller area you're trying to map. So if you're just trying to map Mississippi, and you have that line running down, Mississippi is a longer this way than it is this way, right? Nobody's going to argue that. If you have that line of true scale, and as you get further away from that line, we get less true scale, but it's still not that far away if we're still just in Mississippi. In fact, there is a way to mathematically state how much the maximum scale error is. So it's the transverse Mercator projection, which is a transverse cylindrical projection, is very commonly used in jurisdictions that are longer north-south than they are east-west. Okay? And Mississippi is one of them. In fact, our statewide projection that we've adopted in the state of Mississippi is referred to as the Mississippi Transverse Mercator Projection, or MSTM for short. Okay? That's the statewide projection of Mississippi. If you need to make a map of Mississippi, this is a good map projection to use because the scale distortion is minimized for the state of Mississippi. And there is a published standard, I don't know what it is, but it's probably within less than a meter to scale distortion for the whole of the state, is what I would imagine. I'm not positive, but I could look that up. I should have had that ready. Okay? So you can see this is the transverse Mercator here on the right here. And if you can imagine Mississippi right here, okay, the amount of scale distortion is minimized because the line that has the true scale line that passes through it is just for the state of, just centered right in the state of Mississippi. All right, so this works well for states like ours, for like states like Illinois would use a transverse Mercator projection. Right, and so that if you were trying to make, for a particular jurisdiction, if you were trying to make that jurisdiction have the least amount of distortion, you run it right through the center of that jurisdiction. Yes. Right, so Colorado is a little bit wider than it is tall, but you're right, it becomes more complicated because that state is larger in one of its dimensions. So if one of the dimensions is pretty small, it's comparatively easier to make a statewide projection with less distortion than it is in a larger state like Colorado. Colorado is a little bit longer this way than it is this way. And so they're usually going to use a conic projection like, well, we'll get to conic projections in a second, but they're usually going to use a conic projection because a conic projection, well, I'll go back. Conic projection has these two lines of no scale distortion, so they can pass through like basically at thirds of the state. The other thing that some states do that are really large, like California and Texas, and even Mississippi actually does this. We don't use that projection that often anymore, but they come up with what they call, they subdivide their state. And so they have zones within their state, and that way if you want a really accurate map, in other words, very little scale distortion, you use one of those map projections, and it's centered on just part of the state, and you say, okay, within this zone of our state, there's very little, sometimes even down to the inches in terms of the scale distortion that occurs. Okay? So Mississippi has two of those systems. That's called the state plane system. So Mississippi has two state plane zones, but like California has 5 or 6, and Texas has like 7 or 8 because it's even larger. I'm sure Alaska has a lot more. But those are, we will talk about the state plane coordinate system here in a second. Okay, so yep. Now it is possible to make an askew or an oblique coordinate system. It's not done very often. Okay? It's hardly ever done. In fact, you'd have to press a lot of buttons and to get this into a GIS system. It's not done very often, but it is possible. Okay, we covered that's just showing. I should have put this earlier. That's showing the light source on a cylindrical projection. Okay. So this is kind of an old graphic, but the reason why I leave it in here is because it kind of shows the true scale versus the distortions that are occurring. Okay, there are also other cylindrical projections. One is Miller cylindrical projection, and the way that it works is that the lines of latitude are spaced differently as we go further north to compensate for the fact that the lines of longitude are changing. And so what it does is it compresses the northern part of the world and the southern part of the world a bit so that the areas are a little closer to the real size. Not much closer, but they're a little bit closer. So it's a trade-off, okay? So distance is no longer preserved. It's trying to get some area preservation. World time zones. This is a cylindrical projection. Okay. Planar projections are often used for small areas, and another one was the example I said earlier: circumpolar maps, maps that originate at the top of the or bottom of the Earth. Okay. Oftentimes they're polar, but you can again make an oblique, orthographic, or azimuthal projection. And the difference between those terms is where the light source is. So this would be an orthographic projection where the light source is set at infinity. So it just looks like a picture of the Earth from space. So this is Earth from space. That'd be orthographic. Pretty sure this one's the azimuthal one where it's placed on the opposite side of the Earth. Your book has each one of those. Yeah. So this is the last option. It's called a mnemonic projection right there. So in a Mercator projection, a rhumb line is one of those lines that I talked about. It represents a true a line of true bearing, true direction. So the line from San Francisco to London, it's constant. There's a constant bearing as you follow this line. Has anybody ever flown to Europe here? Okay. When you flew to Europe, did they mention any areas that you're flying over? They did. Like, what are some of the areas that you flew as you flew over the Atlantic? What's that? Ireland. Ireland. Yep. You flew over Ireland. Okay. You actually do take a pretty northerly course like this. Okay. When I was a little kid, I flew to Europe once since then too. But I remember seeing the Northern Lights. You fly pretty far north. Why do you fly this line rather than this line? What's that? The world isn't flat. So this line of constant direction is actually longer on a round globe than this line that's not constant direction. Okay? This great circle line, any great circle is shorter than any other line. The great circle distance between 2 points is always the most direct in terms of distance, minimum distance covered. So this is the great circle from San Francisco to London. Okay? I grew up in Los Angeles area. So that wasn't too different from the flight that I took as a kid. Now this is a mnemonic projection. What the mnemonic projection does, instead of having a constant direction, which is okay for sailing ships that are trying to get from point A to point B, but for airplanes, this one works a lot better. The mnemonic projection, the lines, the great circle lines are straight. These would be good for airplane navigation, particularly ones that are traveling around the Earth. Okay? Particularly one with modern navigation systems that can compensate or change in terms of which direction they're going. All right. Conic projections, as I mentioned, I already said this, used for continent size maps, maps of large countries that take up large portion of continents, such as the United States, Australia, Russia, those type of countries, Canada. All right, conic projections can have a simple tangent conic, or they can be a secant. Oftentimes they're secants, conic projections. And we call those two secant lines standard parallels. So each standard parallel is an area where the distortion is minimized. And so when we make a map of the United States, you want those to kind of pass roughly through 1/3 of the United States from top to bottom. So this would be an example of that. So this is a map of all of North America, and so we're going about 1/3 through the way of the entire map, and a little bit less than 1/3 through there. I don't know the reason for it, but maybe we're more concerned with this area being accurate than this area. That's a conic projection. There's another one. Okay, Robinson is another. Oh, sorry, actually that one is a little bit out of order. Don't pay attention to that one yet. Okay, we'll talk about that type of map projection here in a second. But oftentimes mid-latitude areas are mapped using an Albert's equal area projection. So area is able to be preserved fairly well at the expense of a little bit of conformal. Since we're not measuring the whole Earth, we can come up with a better or a more accurate for our area map. That's really one of the things that happened. Really one of the take-home messages of this lecture is that, first of all, when you're trying to come up with a map projection to use, think about the best one for that area. And the smaller the area it is, the easier it is to come up with that answer. Okay. We already mentioned that. Straight meridians. Yep. We already talked about Mercator. Okay. There are a number of special projections that actually are mathematical in nature and don't necessarily use the same concepts that we've talked about here with the light source and the developable surface. There are some that are made up. In other words, one of them is this Gale-Peters one. And Gale-Peters decided, hey, we want to replace the Mercator projection as the main map projection that gets shown for world maps in schools. I'm sure growing up, like that map on the back of this room, I know you guys can't see it down at golf course, but that's a Mercator projection. Oftentimes, maps of the world for a long period of time, including my childhood, I don't know if it was the same when you were a childhood, were maps like that. Maps of the world look like that map, a Mercator projection. And so Gale-Peters were researchers, and they said, there's things that aren't necessarily fair about that projection. That projection doesn't show, for example, how large Africa is and South America is in relationship to the rest of the world. Okay? And so they came up with a map projection that distorts these areas by basically flattening them even more than that other one. I forgot the name of the other one that I showed you. Flatten them even more. So the lines of latitude are very unevenly spaced. They're wide up here and very narrow down here. And so the areas here are almost true areas. You can see Mexico and Greenland are roughly the same size now, but the problem is that Greenland looks nothing like it really looks like in terms of shape. But this map projection was created to de-emphasize not larger areas, areas that looked as if they were larger than they really were. Okay? So Texas right here is a little more than 2 times as small as Alaska. But on our Mercator projection, Alaska looks like it's half the size of the United States. And it is large, two and a bit larger than Texas, but it's not as large as it looks on the Mercator projection, right? And on this map, I just brought up Alaska. On this map, Alaska, this is not the same map. This is just Alaska thrown onto the, Alaska is bigger than Texas by about 2.5 times. Okay, this map shows a particular set of coordinate systems called the state plane coordinate systems. I already introduced this topic, but each state was tasked with coming up with a coordinate system that would minimize the scale distortion within their state to a certain threshold. And so they came up with these zones. So Mississippi has 2 such zones. Mississippi has 2, Alabama has 2, Georgia has 2. And you can see which states use transverse Mercator projections versus which states use conic projections. Texas went with 1, 2, 3, 4, 5 conic projections. Oklahoma 2, Kansas 2, Nebraska, I guess, was able to get away with using 1. Do you have a question? Yeah, Montana also looks like they just used 1. I don't know. They must have been okay, or they must have been able to have some sort of exception granted, because there's no way to keep the scale distortion within a certain threshold and make it not have any zones in it. So the answer to the question is I don't know. I've never made a map of just Montana before, or Nebraska. But most of the other states have quite a few, or at least 2. One of the exceptions is South Carolina, where I came from before I moved here. So in each of these cases, in each of these coordinates, each one has a coordinate system. This one's based on a conic projection. It has 2 standard parallels. Okay? But something that I didn't go over yet is that your standard parallels and your central meridian are the areas where there's the least amount of distortion, right? Okay? However, those become the x and the y 0 points in your coordinates. Okay? So if I was to just use those x, y coordinates here, the coordinates of the locations over here would be positive, and the coordinates of the locations over here would be negative. That's not really desirable. So oftentimes when coordinates are created, or when a map projection is created, there's what we call a false easting and a false northing. And what that does is allow all the coordinates to be positive. So those are other things. So this is now this was the origin. Now it's over here. So now everything is positive inside the map. Okay. So it's just like a Cartesian coordinate system where there is a real 0, 0, but we've shifted the 0, 0 over to here. So the computer takes care of all the addition and subtraction that needs to occur. Okay. But we can express any coordinate in here as a north and east. In fact, that's how it's done. Rather than using latitude and longitude, now with a projected coordinate system, our coordinates are always north and east from the origin. Okay? Another way to say that would be x and y, right? X would be the easting, and y would be the northern. All right, another universal set of coordinate systems is what we call the universal transverse Mercator coordinate system. So the whole Earth is divided up into sectors that are only 6 degrees wide. Okay, so that works out to be that there are 60 UTM zones. Did I get that right? What's 360 divided by 6? Yes, I did my math right. Sorry. I'm not the best mental math person. Try sometimes. Okay. We're not going to do all these. I mean, ever. There's some slides in here that are just for your personal enjoyment, by the way. If anybody was looking and saw that there's 134 slides. Okay, so with the UTM zone system, we can make a map of any portion of the world. And as long as our map doesn't spill out into another UTM zone, we know that the scale distortion is within a certain threshold. So the UTM coordinate system gets used a lot for maps of just arbitrary areas. So like, let's say you're doing a research project in the Caribbean. Okay? It's likely that whatever country you were doing, unless it's Cuba, is bisected by these lines. So like, let's say you're doing one of either Dominican Republic or Haiti. It looks like the line falls pretty close to the boundary between those two. Or if you're doing any of these Lesser Antilles Islands, you could then use zone 20 to make a map of that, of those islands. Or let's say you were doing South Carolina. South Carolina falls completely within zone 17, which was very convenient for me when I was at South Carolina. We used zone 17 UTM a lot. Let's say you're in Mississippi though. Mississippi is actually bisected. It goes right, the 15-16 line goes right between Mississippi. And that's another reason why Mississippi decided to adopt their own coordinate system, the Mississippi Transverse Mercator System. Okay? So our Transverse Mercator System has a line that just goes right down the center of our state. You can see 15 and 16 boundary. Here's the same map, but this is just for the United States. Right down the middle of 15 and 16. Okay? But South Carolina falls totally within 17. And Utah falls totally within 12. That's where I did my undergraduate. Okay? But if I would have gone to Wyoming somewhere, maybe Wyoming has, I think Wyoming was one of the states that had 3 state lines. They probably have a coordinate system that's for their whole state. I don't know what it's called, but they probably do have that. It might be a conic projection, though. Okay, with the transverse Mercator projection, there are also a false easting associated with that coordinate system. So we got a central meridian and a false easting, and this map just kind of shows you how far off the scale distortion is in different areas. Further, these coordinate systems are actually divided up into north and south. So usually, if we want to specify a particular UTM, we'd say zone 20 north. Okay, that's the one I use a lot for the Lesser Antilles. Okay. All right. So here is 2 different conic projections showing the different standard parallels that are used. 45 and 42 would be used for mapping just the northeast, whereas 45 and 29.5 would be used for mapping all of the United States. All right. Now, I always struggle with which I should have talked about first, coordinate systems or the shape of the Earth. Okay. Remember early in this lecture, I mentioned that we still had to solve the problem of how do we take the Earth and measure it so that we know where the center is, because that's an important thing when we go to make our pretend Earth inside of our computer system, that we have a light source and we project it onto a projection, right? So we can't use the real Earth because the real Earth's too big. So we have to come up with a way to measure the Earth. Well, in order to measure the Earth, we have to ask a few questions and get a few answers. Okay? One of them being the Earth's not a sphere. We already talked about that. The Earth can be modeled, and in fact, most of the time, when we make a map projection, we model the Earth as one of these. We're going to call it a spheroid. Okay? This is an oval, right, on the screen, but if I were to project, if I were to rotate it on an axis, it'd be a spheroid. Okay, it's not a perfect sphere, but it's close to a perfect sphere. It's wider this way than it is that way. The Earth actually, and this is a big exaggeration, the Earth actually looks like this. Not really. What I'm trying to say is the Earth does undulate, and I'm not just talking about the fact that it has mountains and whatnot. It actually isn't a perfectly round circle. And the way that we measure this is through gravity. Okay? Everywhere you go, you can measure what's straight down using graviometers, which direction is straight down. You can use that, and you can find out that the Earth actually has bulbs areas where it sticks out and depression areas where it sticks in. Okay? You can't measure that by observations other than using measuring the force of gravity. Okay? Because water will actually follow the gravity, and so it'll appear as though the water line is actually the same even when it goes in. All right. So a little bit of history on how the Earth got measured in the first place. You need to find out how big it is, what the shape is. Okay, way back before the Middle Ages, this was the time of Greek Empire. This guy in Egypt discovered that at the same time, he noticed that parallel rays from the sun reached the bottom of a well at one point, but had an angle associated with them at another point. Okay, and so he used that to make a measure of the Earth. Okay, and he was actually pretty accurate in his measurement of the Earth. Okay? And that stood for a long time until we discovered that the Earth was not exactly circular or spherical. And so what we do today is that when we want to express the Earth as an ellipsoid, that was basically a rotated oval. We have to have two measurements. A sphere can actually be just defined by one measurement, its radius, whereas an ellipsoid is defined by the semi-major axis, which is, think of it as the larger radius, and the semi-minor axis, or the smaller radius. So most of the time when we do cartography in computers and we have a coordinate system, we're using the ellipsoid, and the way we specify the ellipsoid is using these two numbers, the semi-major axis and the semi-minor axis. Sometimes all we do is have the flattening ratio, which is basically a minus b over m. And most of the time, if we use a standard coordinate system, we don't enter those values ourselves. Okay, but I'm telling you this for background, right? There are lots of different measurements of the Earth that have taken place over time, okay, through different time periods and for different parts of the Earth, okay? Now, the Earth is the Earth. Why am I saying different parts of the Earth? Well, if you think about this circle, or this ellipsoid, if the Earth really is a shape that looks like this, let's see, if the Earth really looks like that, but we're modeling it as this, if we're just concerned about a little piece of the Earth up here, then we might come up with this ellipsoid that passes the best through just our portion of the Earth. And so sometimes there's been ellipsoids that have been measured with the idea of just part of the Earth being all that we care about. Okay? So they have different, so this one is Australian National, South American, Clark. These are all worldwide. The WGS is the most recent worldwide one. And there was one in 72 and again in 1984. Now, a spheroid, the measurement of the shape of the Earth, is necessary regardless of whether we're using planar coordinates or geographic coordinates. So when I get, going way back to the beginning of the lecture, when I get my latitude and longitude, say from a GPS, that number will be different based on how I'm modeling the Earth, which ellipsoid is being used. All right, now, just the ellipsoid isn't the only thing that determines the shape of the Earth. Also, the tie point, or where the reference point is that attaches this sphere to the real Earth. And that tie point, together with this ellipsoid shape, together those form what's called a datum. Okay? So datums can be national if we're just concerned with a certain part of the world, or they can be global if we're concerned with the world as a whole. So the WGS 84 is a global datum, and it's pretty much, like if you just turn your GPS on, that's pretty much the one that's going to show up. However, if I go do research in Jamaica, they actually have, they call it JAD something, I forgot what year it is, it's early 1900s. Most of the maps are using that Jamaican, I forgot what the A stands for, maybe it's just Jamaican datum of whatever. Then that's what they use as a reference surface. So every coordinate system has a datum associated with it that is expressing the shape and the tie point to the Earth, every coordinate system, whether it's geographic or whether it's projected. Okay? The difference between the projected coordinate system is it takes it the step further. And the step further is that it also has some sort of either lines of some sort of the lines of parallel or the lines of tangency running north and south if it's cylindrical or latitude and longitude. Okay, so different governments, including the United States government, spend a lot of time measuring the surface of the Earth. So they get measured and changed over time. You might have seen something like this. This is a benchmark. You can go look up this benchmark number and find out what its calculated coordinates are for various periods of time using various datums. All right. Kind of talked about that. Semi-major axis, semi-minor axes, ellipsoid. All right, one other thing that I want to talk about. We can actually measure the shape of this is what we call the geoid. The shape that's, geoid actually means Earth-shaped. So the Earth is Earth-shaped, by the way. We can't actually measure that, but we do that through gravity. Okay, graviometers. You can take them, and so the highest point on the geoid above the ellipsoid is in New Guinea. And we're not talking about elevation. We're talking about the position on the Earth where gravity is a constant value. It might be higher or lower. If you go up higher, gravity, the higher, you have to get to 75 meters above the ellipsoid in New Guinea to get to the same gravity value that you are at when you're 104 meters below the ellipsoid, the WGS 84 ellipsoid in India. So you're totally above and below the ellipsoid. Now, this doesn't really matter too much as cartographers. There are things where this is very important. Okay, the geoid height matters for things that measure gravity and mean sea level and things like that. If we're talking about floods and things like that, you might have to get involved in it. But if we're making a thematic map, most of the time, all the time, we express the shape of the Earth as an ellipsoid. So we're using ellipsoids. You can't make a mathematical model of the geoid, okay, because it's the real shape of the Earth. It's too unpredictable to make a mathematical model that would be accurate everywhere. And so the ellipsoid is the mathematical model of that shape. So the geoid is a measured surface. It's not mathematically defined. You get it by taking measurements. Okay. Here's a graphical measurement of that. The geoid is undulating. The Earth's surface, which isn't the same as the geoid, is also undulating. We've got mountains in some place and valleys in others. The geoid is the location where gravity is constant. However, the ellipsoid is always a smooth surface. It's the modeled surface of the Earth. So maps are models. We use the mathematical model of the Earth when we create an ellipsoid. Okay, so this is just a map of the geoid values as they deviate in different areas of the Earth. So here's 0, but here we've got values of negative 80. In other words, much below the ellipsoid. Positive values, there's 40 above the ellipsoid. So here's a bunch of official ellipsoids. WGS 84 is the most common one. It's not on this map, not on this one, but these were old ones. Okay. All right. So the Earth's not a sphere, and so a spheroid or an ellipsoid is parameterized to coordinate a datum. So we need, in order to get a datum, we have a spheroid and how it's tied to the Earth. That's how we get to a datum. In order to have a projected coordinate system, we need to have a datum, and then we need to have the set of standard parallels or some other projection that take the paper and develop it into the Earth and develop it into a flat surface. So that's kind of the take-home message there. All right, now what kind of effect can this have on maps? Well, sometimes when you're using GIS, you will open up 2 different data sets that should match up, and you'll say, these data sets don't align. If you see alignments that are constantly off, but are only off by meters, maybe sometimes tens of meters, maybe even 100 meters, then those would be datum shifts. You see 2 sets of maps and they don't line up perfectly. It's because you've got 2 different datums that are being used. It's not a difference in projection in terms of the projection coordinates. In other words, if your standard parallel was different, they wouldn't even match up at all. They'd be like in different spaces. More likely, so there's all sorts of things that can change. One of them is datum. Datum shifts look like this. Okay. What if your map was this? Let's say this point has a coordinate of 3, and the same point in another map has a coordinate of a little bit over 3 times the amount, like 9 something. Okay, it's the same coordinate. That is a, what's that?
Scale.
Scale is one way to say this problem, but it's a unit problem. One of your maps is probably in inches, and one of your maps is probably in feet, and one of them is in meters. Okay, because you're off by about 3. So if you see 2 maps, you zoom to the full extent, one's here, and this one's 3 times larger, you're probably off by, that's not a datum issue. That is that's a scale or a unit of measure issue. Now, if you really can't tell what the deal is, in other words, if there doesn't seem to be any method to it, that maybe they're the exact same size, they're just in different parts of the Earth or very close to the same size, then that is probably a projections issue. They're in 2 different projections. Okay. All right. So here's another datum shift, datum offset. Okay. Now, we're going to do this in the lab today. So maybe I'll just go over this really quick, and then we'll take a break, and then we'll do the lab. Okay. ArcGIS, everybody had an opportunity to use it last week. Most of you.
And, I took the map, something comes up, it's like a little red exclamation point next to both pictures. And we fixed it at one point, but then when I came back to do the rest of it, just went revert and skip back.
Right, okay. So I'm not going to go over that. Basically what happened was your data disappeared or was moved. So we went over that in the lab, but I'll go over it again. So the map document doesn't actually hold the data. We'll go over that when we get into the lab. But anyway, when we load data up into ArcGIS, the data itself has a projection associated with it a lot, but not all the time. And so if you load up a data set A that's in projection A and data set B that's in projection B, ArcGIS nowadays, not when I was an undergraduate, but nowadays, it will take those two and it will perform the calculations it needs to make those two overlay. In other words, it will do the math to convert data set B into coordinate system A. Because that's one of the things GIS systems do, is they change coordinate systems. All right? Now, that's kind of cool. However, what if you load a data set that you created on your own that doesn't have a coordinate system attached to it yet? Well, then it's unpredictable. Then it'll probably do something like I said, show up in another place. And there are other tools that we don't really go over in this class, but we do in the GIS class. If you ever have these problems on a lab that you're working on, just let me know. There are other tools to say, this data set that I have is in projection X. So when you do projections in ArcGIS, there are two different tools. One's called define projection and one's called project. Define projection is the tool where you're saying this data set is in projection X. It doesn't change the data. It just proclaims that that data set is in that projection. And so if you proclaim that it's in a projection and it's not the right projection, you're just going to confuse the program. However, if you use the term, if the data already is in a projection and it knows that it's in the proper projection, and you say, I want to take this data set and I want to convert it from this projection to this projection, project is the right tool to do that. So many people get those two tools confused or don't understand the proper application of those tools. So it is possible that you bring up one data set in your computer and it looks like this, okay? But nowadays, the only reason why this would happen is because you've told both of these data sets they're in NAD83, when in reality, one of them is not in NAD83. So if you use the define projection tool to tell this one that it was in NAD83 and this one that it's in NAD27, or other way around, sorry, NAD83, NAD27, then if you open them up in modern GIS software packages, they would line up perfectly. Okay? So they don't need to be in the same projection anymore to line up. So if you see something like this, it's because someone has used the define projection tool wrong. Somebody has basically said, this is in NAD83, but it's not. Okay? So when you see a data shift, it's the first thing you need to identify is which data set is not projected correctly. And the way that I do that is bring in some other data that I know is projected correctly, and I find out, does this data set match it, or does this data set match it? This data set matches it, and I know this one has been told it's in the wrong projection. This one's in the right projection. Okay. Another nice thing that this means is that when we're making maps as cartographers, often it doesn't matter what projection our coordinates are in. We can change the coordinates of what we're viewing. So we could have 10 different data sets and 10 different projections. We could bring them all into ArcGIS, and we could display them in a 10th different projection, or 11th different projection. Okay? We could change the projection really fast. It's just one button. Drop down, well, a few buttons. But change the projection We open it, we press a few buttons, we change the projection, we see it, okay? There are tools for changing the projection of the data itself, but oftentimes as cartographers, we're more concerned with just displaying it in the right projection. A data set will display faster if it's a very huge data set, if it's in the same projection it's being displayed in. But that's really not a concern unless it's a very, very large data set. Okay? I'll go through each of these when I go through the lab, when I introduce the lab here in a second. So let's take like a 10-minute break, and that'd be at 2:45. And at 2:45, I will introduce the lab, and then Chris and I can answer your questions. And Corey down there on the coast. Okay. Everybody gets a unique authorization. What's your email again? Sure, or just send me an email. Say, hey, I want to. I have the authorization. So send me an email and I'll get it sent.
It's the third year.
Well, I was in this class last fall. We turned it in, but it was over, so I didn't see it. I did make those. Yeah. Hopefully,
Probably because you know how to reset the rest.
Yeah. I'm really on last year.
Try.
Let's not go scare me down again.
It just doesn't even open.
Yeah.
It's just not opening. Anybody else having trouble opening ArcGIS?
I do have a question now. The exercise questions that are below
Yeah,
everything, do we need to put those in?
yeah, just email them or in the body of the document or as a separate tab.
Okay, do you want us to email it to the administration tables?
Yeah,
And we have,
preferably the same one email, like with the attached image and either the question in the body or as a separate attachment.
do we have 2 weeks after every
Yeah, 2 weeks after every line. That's correct. You showed up. Yeah, well, there is so this GHY@usm.edu is running the license manager. I don't understand why it's running there, so let me see which one it is using.
Oh, yeah, I did this. I have like just
And you're able to see other things on the internet? That's the problem. Is that it needs to be online. I wonder.
Yeah. Yeah. Of course.
Check my go on web browser or something. You go to you go to another website. Just go to any website. How about now? Okay, now try to start up here. I don't know exactly, but the internet cable stopped working or something. All right, sorry about that. All right, so one of the things that I just want to demonstrate is, first of all, now that I'm using this computer, I'm running 10.4, so things might look slightly different, but again, they're going to look pretty similar. Okay, projections. I'm going to double click on this projections.arcmap doc. You don't have to do this because I'm demonstrating something that's not going to work. I just downloaded the zip file, and I went into the zip file, and I double clicked on projections. Okay, now what's going to happen? It's not going to work. What do these little red exclamation points mean? The data's not in there. The data can't be in there, right? The data cannot be in there because they're all still zipped up in this zip file. They're all still zipped up in the zip file. So the first thing I need to do is to take this folder and copy it to a location. Now that I'm on my laptop, I don't have a whole lot of locations, but I just have a C drive. So I'm going to set up a new folder, call it and then paste it in there. Okay. So now I have projections, and I can open up that projections file. I just extracted it. There are like literally 10 ways to extract something out of a zip file, but you need to do one of those things. different ways. You can do what I just did. You can copy and paste it, the whole folder, the projections folder that's inside the zip file. You could extract it all. That's the method I showed you last week. So for extract, you could go to this folder that was this file that was downloaded. You right-click and say extract all. That's one way. The only time we had a problem was that some of the machines have WinZip installed, which is no longer licensed. I don't know how that got installed on there, but it's kind of a pain if you did that. If you have that, not that you did that, you didn't do it, somebody else did it, but double-click into it, copy, and paste it to a different location. That's what I did, okay? So that's one way to extract it. Now that it's extracted, I have it, I open it up in ArcMap, and now I can see everything. I don't have the red exclamation points. All right, another thing I'm going to show you. Don't do this, okay? What happens if I move just this projection file? I copy this. I talked about this last week, and I paste it in here, or I take it home with me. Then I try to open it. What's going to happen? It's not going to work. I get the red exclamation points again. Why do I get the red exclamation points? Okay? It's because the data didn't get moved in addition to the MXD. So this folder right here, this is your MXD file that opens up an ArcMap. But this folder contains a bunch of data. And they have to be moved together. Wherever you're going to move them to, they always have to stay together. They're like buddies. If they don't stay together, you'll get the red exclamation points. Another way to drive this home is if I right-click and say Properties, and I go to Source. Okay, maybe I went a little too fast there. We can go back and look at the video. Right-click, Properties, Source. It's looking for them in C-Cart project data. Okay? It's looking for it there. They're not there. They're not in project projection data, sorry. Because there's no folder called projection data in there. C-Cart projection data. Now there's one level down. So what I could do a few things. One of the things I could do is take this projections data folder and put it at the same level. Remember, if I keep them together, it should work. So now they're buddies. They're in the same folder, and when I open them up, it works. Okay. So now I have two copies. I'm going to go ahead and close this down. No. I have two copies. One's in here, one's up here, but I could put them anywhere in the world as long as they're together. They need to be together. If they're not together, they won't work. Or if I went in here and deleted all of this, it wouldn't work. Okay? This is necessary data. This is the projections data. So now I'm going to open this up for the third time. I'll also open up the lab. So in the lab now, there's a bunch of information that's good to read over. Okay? You're going to take this data and you're going to display the data in different coordinate systems. So right now, can anybody tell me really quickly from the lecture what coordinate system is being displayed here?
UTM.
That's a good guess, because UTM did look kind of like this, but the UTM map was, what's that? No, it's with the Gale Peters. Okay, are latitude and longitude lines the same distance on the map? No, on this map. Every line of latitude and every line of longitude, all the squares are square, right? All those squares are square. Okay, so this is just a geographic projection. Lines of latitude, lines of longitude are the same. They're the same exact size on the map. They're all the same size. Okay? You haven't learned this yet, but another clue is that this is displaying degrees, minutes, and seconds rather than displaying latitude and longitude down here in the right corner. See that? So when I move my mouse around, I'm seeing the coordinates as latitude and longitude. So this is a geographic projection. Okay? I can go in to I can click on layers, right click, and say properties. And then I can go to coordinate system and it will verify this. It's telling me that this is a geographic coordinate system, GCS. And it's using the datum WGS84. Because remember, to specify a geographic coordinate system, all I need to specify is the shape of the Earth and a tie point, in other words, the datum that's associated with it. Okay? Because once I establish the shape of the Earth, that defines where the center of the Earth will be. And then from that point, I can do latitude and longitude, because all I really need to know is the center of the Earth and how it ties to the Earth. So, not that you'll, as a cartographer, not that you'll need to know all of these individual values. You won't need to pull these out of a hat, okay? But somebody's figured this out, and so it's great that it exists. But you can see what the semi-major axis, the semi-minor axis are, and you can see what the flattening coefficient value is. It's 298 point something. Okay, these are the parameters for the WGS84 datum. Okay? Those are the parameters for the WGS84 datum, and the WGS84 datum, like almost every datum, uses the prime meridian as its 0, 0. That's all that's telling you. This WKID it stands for, actually, I don't know exactly what it stands for, but it's the well-known ID. That's what WKID stands for. The well-known ID, in other words, it's the standard ID adopted for this coordinate system, 4326. I don't know a whole lot of well-known IDs, but I do know a few. That's one of them. So latitude, longitude, geographic coordinate system. That's what we got here. Okay? Now, what I can do is I can change the coordinate system of this display. And that's one of the things you're going to do. So see the data here. This is the data. Okay? Once I've opened up this window, I can change the coordinate system. And this dialog looks slightly different in different versions of ArcGIS. But if you can go down, there should be the choice in every single one to choose between geographic coordinate systems and projected coordinate systems. So I can go to projected coordinate systems and choose a world one. We'll choose one that we've been doing a lot, and that's Mercator. We've been talking a lot about. Where's Mercator? LMN. There it is. Well, there's Web Mercator. There's World Mercator right there. Okay? WGS84 World Mercator. So now I say OK, and you can see how the projection changed. Okay? So you might say, well, the Earth looks different now. What's the advantage of using this projection? Well, we already talked about that in the labs, in the lecture. The advantage are that shape and therefore direction is preserved fairly well, at the expense of area. Area is now widely distorted. All right, so that's changing it. I think I can do another one. Let's do. I think the world from space is on here. This is an orthographic projection. So I say, OK. Yes. When you see that, just say, OK. It's just basically warning you that it's going to be projecting data. OK. So now I've got the world from space, and I can see North America and South America. I can't see China anymore. What if I wanted to see China? What if I wanted to put China, I wanted to be away from China and see China rather than seeing the United States? Well, that involves modifying the projection a little bit. You're going to be, the lab walks you through doing things like this. But what I can do is I can take this coordinate system, and what I need to do to modify where it's centered on is change these parameters right here, the longitude of center and the latitude of center. Okay? So I can edit this. Oh, edit. There we go. Copy and modify. The world from space _ China. All right. And so my new latitude of origin is still going to be in the northern hemisphere, but it's going to be down just a little bit, I think. I'm going to choose like 30. And my longitude of center, anybody know how far east China is? Let's start with positive 72, just going from Greenwich the other direction, 72 degrees. I don't know if we're going to end up in China, but we'll see. Okay, so I'll say OK. And this is my custom projection. And I say apply. I didn't get like right in the middle of China, but I got close. Okay. I'm kind of more over India. So I modified the center of that projection. I can do that with any projection. I could take a UTM projection and center it anywhere. I could take any of the projections that are in there and modify some of the parameters and center them in a different location. So as a cartographer, that's something that you might need to do. Like if I wanted to make a map of this side of the world, that's the only way to do it. There's not like 20 different the world from space projections. They all default to being over the United States because the software is U.S. centric. I mean, it's developed out in California. So now I could use this to map, Asia and publish it in a magazine. Or let's say that I was concerned with just like Southeast Asia and this area, then I might want to recenter it like that. I just need to find out what the center is, and I can center this map anywhere I want, and be effective, make an effective map in doing so. All right. Now here there are these circles that we're not turning on, but this is another thing that you're going to turn on. So you can see the distortion that's occurring. That's what the purpose of the circles. The circles are perfectly circular if I go back to the GCS. And by the way, if you ever want to go back to the GCS, it's under World, WGS 84, and then you'll have it there. Okay. So there are perfect circles on the globe, on the world from space. Not the world from space, the GCS. All right, so what are you going to do? Well, starting out with this, and you're going to basically play around with changing the coordinate system like we did. You are going to do North Pole equidistant. You're going to do Albert's equal area conic projection. So this is a coordinate system that's very useful for just Asia. Okay, so it's a lot of distortion in the other parts of the world. In fact, a lot of these maps here, I'll show you MSTM what it looks like. So MSTM is under Mississippi Transverse Mercator. Is under state systems, projected coordinate systems, state systems. And let's see, where's Mississippi Transverse Mercator? Okay, now you notice this one is named NAD 1983. There's a bunch of numbers, Mississippi Transverse Mercator in meters. So this one is basically, that stands for North American datum. And the North American datum was based off the WGS 84 big datum, but it's a little bit different. Okay, it's made just for North America, optimized for that. So when I do this projection, it basically just cuts off most of the world because it'd be ridiculously, like I said, it would look like a butterfly. It'd just be ridiculously large. But for Mississippi, this is a great projection. Mississippi's right down here. All right. That's not part of the lab, but I thought you'd want to know where that is on there. I'll go back to, oh, and another thing, you guys said UTM at the beginning. The map, this map, right? Oh, I already closed the PowerPoint. But the map of UTM zones was not a UTM projection map. The UTM maps look like this. Okay, this is a transverse Mercator projection. So if I choose UTM for zone 20, which is out there in the Caribbean, it's a good one for the Caribbean, then I'm going to get the same thing but centered over the Caribbean, okay? Centered over this area. So this is what a UTM map looks like. UTM's not meant to show this much of the world. Okay, let's say I was making a map of just St. Lucia. I wouldn't use this data because that looks silly, but that would be a good map projection to use. Okay. All right, so you're going to go through here and do a bunch of different projections. And there's a Robinson. There's a hard projection. Very cute. There's a star projection too. All right, and then the final thing that you're going to do is to basically create a world from space map that's centered on your hometown. If for some reason you're like, I don't want to tell George where my hometown is, I don't really care. I'm not going to look up your hometown. So you could claim a different area as your hometown. Okay, so but really there's no reason to not use your hometown, but or your birthplace or whatever. But it should be oriented on that. Okay, so how do you find the coordinates of your hometown? Anybody got any ideas on how to do that? What's that?
It gives you a website and instructions.
Yeah, it gives you a there's tons of websites. I'm not the only one. You can just Google, find the coordinates from a map click, and then there'll be a website. But you can also use that one. All right, good. And then I noticed some of you have done this for this class. You go to export map, you save the map of your hometown, centered on your hometown. You still want the whole world from space. So basically, the world from space, like I did for China, you're just going to do it for your hometown, okay? And then that's the only map you actually have to hand in. You don't have to hand in all the little maps if that's a question anybody has. But you are going to be answering some questions that will be answered better if you've gone through the entire exercise. All right. Now, just like any other class, you have 2 weeks to do this, and Chris and I can answer any questions that you have, and Corey down there on the coast. Is Corey there? Good.
Okay.
Great. You have a question right now?
Yes.
Okay, go ahead.
Will you be responding to the emails about a code to download the personal copy of our GIS?
I have. What's your name?
Mark Gillespie.
Okay.
I sent an email Friday.
Okay. I guess I missed it. Did you send it to george.raver@usm.edu?
I did.
Okay. All right. Well, let's take care of that right now. How do you spell your last name?
Gillespie.
I didn't get all that. Like Gillespie? Like that? It starts with a what? Oh, M-A-R-C. There we go. Is there anybody else that didn't get a response from me? I mean, I got like, 15 or 20 emails, and I guess I missed. What's that? If anybody wants the code. Okay, I can do that right now. Just a second. Yes.
If you have a Mac, do you know of any type of freeware you can install to run Windows?
Freeware. Well, Boot Camp is not free by Mac. I thought Mac's.
I talked to Dr. Carr, and she said that when you have to run ArcGIS on Windows.
You do.
And she suggested VMware, but I looked it up and it's actually $2.
Okay.
So I just wasn't sure.
I think Boot Camp. I'm almost positive Boot Camp. It's called Boot Camp, and it is free. The only issue with Boot Camp is that you actually have to reboot. You're either in Windows or you're in Mac. So yeah, if you install Boot Camp, you have to reboot your computer, and it'll give you the choice to boot into Windows or boot into Mac. Now, VMware and Parallels is another one. Those do cost, and those allow you to be in Mac and then like open up Windows as a separate, like a separate window. You can full screen it if you want, but it's still a computer within a computer. Does that make sense? But Parallels, I had a Mac like 4 or 5 years ago. Not Parallels, Boot Camp. We'll just basically partition part of your hard drive and make it Windows so you can boot into Windows. What's your name again?
Brittany.
I've emailed you before when you were sitting in my office. Okay, how do you spell it? What's your email? Tell me how to spell it.
MCCAL.
Where did I put my email? Oh, it's right there. So the instructions are on Blackboard, but that's the code. Okay. Anybody else need a code? I can do it right now. All right. Please tell me your email address.
Kendall,
Kendell.
ALL. Dot Junker. JUNKER. Yeah.
No problem. Now follow the instructions because you do actually have to register this code online before you you use it. Follow the instructions that are in there. All right. Spell it, sorry. What? All right, did somebody else raise their hand? Either on the code store here, codes? Yeah. What's that? It might help because it's hard to tell on the screen who everybody's face is for me, especially since I don't know everybody yet. But yeah, that'd be great.
Okay, I mean, I wasn't sure if you really cared or not. You know, if you wanted, I can get in class, I can send around a piece of paper and you can always sign in, just email you that.
Yeah, that'd be great. But we don't need to do it all semester. Just for the first few few weeks. Yeah, I actually turned in the to not attending. Everybody was attending last week, so I marked everybody as attending the first week. That's registered for the course.
Some professors don't really care, some professors kind of want it.
Yeah.
I mean, I think it's kind of on them to get the work done and not get paid.
Right,
But-
right. Yeah, I agree. I don't take attendance the entire semester, but it would be good for me because I'm not down there maybe just this week and next week.
All right.
Just to let me know who attended and start associating the people that are in class.
Yeah, completely. All right.
Thank you. Anybody else want a code? What's your name? Your email, sorry. DEREK? DEREK at, Duckworth. At USM? Okay, can you still access that? I know those are going away. I'm gonna send it to both, Derek. So whichever one it gets to, it gets to. It only runs on Windows, but Boot Camp is a free software provided by Apple. So you can boot an Apple into Windows, but you have to have a Windows license to do that. And I'm pretty sure, am I wrong? Does anybody know if you can get a Windows license through the university or not? You can. I think you can now. I think it just started. Right. But do you get Windows itself? Okay. Yeah. It's a new I think you get 5 of each license though. It's not unlimited. Anybody else need a code? All right. Email address? ELLEREV. Yeah. ELLERVE. Okay. And this code, the directions are online. This code allows you to install the software on a Windows computer. So, all right. Any other codes? Any other questions? All right. Any question? What's that? Okay, so you can just go. I guess your bar. There it is. Well, I want to take this and put it right there. Right on the table right here. And then go up and over. Main menu. You go right there. Right there. Somehow that got forward. So now you have file saved. It'll save in the same location, or you can go save that if you want. Now, the way that you send it to me when you're done, the picture is you go to File, Export Map, and then it'll create a PDF. The directions for that are in the lab. I'm going to shut this down now.